All right, I'm going to begin section 3.2 now, which is called measures of dispersion. That's really just kind of fancy words for a few things that we'll be talking about. So the first thing is range of a data set. The range is very simple to find. All you do is take the largest value minus the smallest value. We're also going to talk about the variance and the standard deviation. Now, the standard deviation will be very, very important to us as we go on through the rest of the course. Okay, the variance is something that leads up to the standard deviation. In a data set, the difference between an observed value of a variable and its mean is called the deviation about the mean. Okay, so it's the difference that a value is from the mean. Okay, now the standard deviation of a variable is a number that is meant to describe how much spread is in all the data values. The bigger the standard deviation, the bigger the spread. The smaller the standard deviation, the smaller the spread. It indicates how much on the average each of the values in the distribution deviates from the mean of the distribution. So deviates means spread out from the mean. In order to compute a standard deviation, we must take the square root of the variance. Okay, the variance is defined as the average of the squared deviations from the mean. Okay. The variance, quite honestly, is very useless to us. Okay, but in order to get the standard deviation, we need to go through the variance. So I want you to think of the variance as kind of a stepping stone in getting the more important thing. Okay, the standard deviation really, really important. Okay. So a definition there: let x1, x2, x3, all the way up to x sub n be a group of capital N numbers in a population, and let mu be the population mean. Okay, in the last video we talked about how capital N is usually a preferred symbol for representing population stuff, and a small n is usually a preferred symbol for representing sample stuff. Okay, so keep that in mind. The population variance, which we're going to call sigma squared, this is in your book, is given by sigma squared equals x sub 1 minus mu, the quantity squared, plus x sub 2 minus mu, the quantity squared, plus x sub 3 minus mu, the quantity squared, plus all the way up to x sub n minus mu, the quantity squared. And you're going to divide that all by n. Okay, so once you get the mean, you're going to subtract the mean from each value, and then square each value, add them up, and then divide by the total. The symbol sigma is a Greek lowercase letter, okay, and that symbol represents the population standard deviation, okay, and how we get the standard deviation is we need to take the square root of the variance, okay. So like I said, think of the variance as just kind of a stepping stone in order to get the more important thing, okay. Now, just like with the mean, we have population stuff and sample stuff, okay, and you need to make sure that you get the correct symbol there. Let x1, x2, x3, x all the way up to x sub little n be a group of little n numbers in a sample, and let x bar be the sample mean. Then the sample variance, which we're going to call s squared, is given by s squared equals x sub 1 minus x bar squared plus x sub 2 minus x bar squared plus x sub 3 minus x bar squared plus all the way up to x sub n minus x bar squared divided by n minus 1. Okay, now when I compare these two formulas, they look the same. The only difference is the denominator. Okay, whenever we're told that we have a sample, we need to subtract 1 in the denominator when we compute a variance. Okay, now that's not something that we really need to know, although your book kind of talks about that further, is to avoid what's called a bias statistic happening. Okay. But so, and by the way, you only do that when you compute a variance, okay, not when you compute the mean. So the mean is the mean, you know, regardless of whether it's a population or a sample, you're still going to add up the numbers and divide by the total, okay. The sample standard deviation, S, is found by taking the square root of the variance, okay, so just like with the population variance, all we do is we take the square root and we get the standard deviation. Okay. Note The larger the standard deviation, the more dispersion the deviation has. Dispersion is the degree to which the data values are spread out. Okay, so the more spread there is, with a bigger standard deviation. As an example, suppose I give a stats test to 30 kids, okay, and scores are ranging from 20 to 30. Okay, now if I compute the standard deviation, by the way, that's always going to be some non-negative number, okay, and if that's a larger number, then when, if, like, suppose I give the same test again, and but this time to a group of 30 different people, but this time scores range from 70 to 95. Well, if I compute the standard deviation, I'm going to have a much smaller number because the values are not spread out as much. Okay, so that's what the standard deviation means to us. Okay, is the degree to which the values are spread out from the mean. Okay. Here's an example, problem 6. So we're going to treat the following data we're going to treat this as a population. Okay, and the following data represent the pulse rates in beats per minute for 9 students in a statistics class. Okay, so there's our students and there's the pulse rates. And we compute the range. Okay, the range again is very simple. All you do is you take the largest value, 90, minus the smallest value, 64. And we got a range of 26. Okay, now 26 is not too big of a number, not too small of a number. So when I compute the standard deviation, I shouldn't expect some really huge number or some really minuscule number. If I get either one of those two extremes, something went wrong with the calculation. Okay? Now the first thing that we need when we find the standard deviation is the mean, because we're subtracting the mean from each value and then squaring the result. Okay, so to get the mean, I need to add up the 9 numbers and divide by the total, 9. When I add up these 9 pulse rates, I get 709 divided by 9. That's roughly about 78.8 if I go nearest one digit. Okay, now sigma squared, so the bulk of the calculation is going to be in getting the variance. Okay, sigma squared. So sigma squared is where I take, since I've only got 9 numbers here, I'm going to go ahead and write a 1/9 out front. That way, just to avoid having this look silly, like where I got some huge thing and then I got underneath, a dinky little number 9. Okay, so it's easier just to write a 1/9 out front to take care of that. Okay, so the bulk of the calculation is going to be in getting the numerator. I need to take each value minus the mean squared. Okay, so the first number, I get 88 minus 78.8 squared, and then plus 75 minus 78.8 squared, and then plus 68 minus 78.8 squared, okay, plus etc. And I continue to do that until I get to the end. Okay, so there's 88 minus 78.8 squared, okay. I include brackets around that because I got 1/9 times this whole thing. Okay, the brackets are a necessary thing. Be sure that you got that. And so now I continue to simplify here. I got 1/9 times. So when I take 88 minus 78.8, I get. Let's see here. So 88 minus 78.8, and then squared is 84.64. Okay, and that's what I got there. Then the next one that I take is 75 minus 78.8 squared. Okay, so 75 minus 78.8 squared gives me 14.44. Okay, which is what I got. Okay, then I take the next one, which is 68 minus 78.8 squared. So 68 minus 78.8, okay, squared 116.64. Okay, and that's what I get. And by the way, since I'm squaring each one of these results, I will never have a negative. I see that sometimes the students have a negative there. They don't know what they're doing wrong. So you will never have a negative when you square a value. Okay? Now, when you add up these 9 values here, you should get 853.56. Okay? And I need to divide that by 9. Okay, so let me do that. 853.96 divided by 9 is, 853.56. 853.56 divided by 9 is 94.84. Okay? And by the way, notice how I'm using the equal sign here, so I've done no rounding in this, except for the mean, okay? And now when I take the square root of 94.84, that's going to get me the variance, okay? So I take the square root of 94.84, I get roughly 9.74, okay? So 9.74 is the standard deviation. That would be my answer to part B, when I compute the population standard deviation. Okay? Now, by the way, that to me sounds right. The reason is because, so this number, 9.74, is not some super huge number, and it's not some really minuscule dinky number, really very close to 0. Okay? I didn't get either one of those two extremes. And that should make sense because the range was 26. The range is not a super huge number, and it's not a really dinky number. Okay? So you can kind of have an idea of what the standard deviation is based on the range. Okay? That, by the way, the bigger the range, the bigger the standard deviation. The smaller the range, the smaller the standard deviation. Okay? And just to kind of tie this in with the boundaries, so again, what this means is this is the average spread in all the values, all 9 of these values from the mean. Okay, so if you're sitting at the mean, 78.8, and you go 9.74 units to the right, that brings you to 88.54. Okay, well, the biggest number that I had was 88. So, okay. Now, if I'm sitting at the mean, 78.8, and I subtract 9.74, I get 69.06. Okay, well, the smallest number that I had was 64, right? Excuse me, the biggest number that I had was 90. The smallest number that I had was 64, right? So I'm within my range, okay, which is good. You know, so the average spread in all 9 of these numbers away from the mean is roughly about 9.74 units, would be the translation of that. Okay. In part C, we want to find a simple random sample of size 4 and compute the sample standard deviation. And then we'll answer, is this an overestimate or an underestimate of the population standard deviation? Okay. You know, to have this be a random thing, suppose I use my random number generator in the calculator and I generate 4 numbers randomly. So I go to rand int and I hit 1, 9, I hit enter, and the first number that comes up is 8. Okay, so the 8th number would be Erica, that'd be the first pulse rate that I'd use. Suppose I hit enter again, the number 6 comes up. Okay, so Abby's would be the next one, and I hit enter again, the number 2 comes up. Drew's would be the third one, and I hit enter again, and the number 3 comes up. Okay, so Tyler's would be the last one. So these 4 numbers would be what I get randomly, and now I need to find the variance. Or, excuse me, yes, so I need to find the standard deviation, right? And the first thing I need to do is get the mean of these 4 values. Okay, so if I add up these 4 values, I get 296 and then divide by 4, and that gives me exactly 74. Okay, so the average pulse rate of these 4 students is 74 beats per minute. Now, the next thing I need to do is I need to get the variance, okay? So I need to take each value minus the mean squared, and then I need to divide by 3. Why am I dividing by 3 and not 4? Well, it's because of how we define a sample standard deviation. We need to divide by n minus 1. So n represents the sample size. So here I've got a sample of size 4. 4 minus 1 is 3. Okay. Don't make that mistake. I see students do that where they have a 1/4 and it should be 1/3. Okay, because they didn't subtract 1. Remember, you only do that when you find the sample variance, not the mean. Okay. So when I take 67 minus 74, I get negative 7 squared. It gives me 49. 86 minus 74 is 12. 12 squared is 144. 75 minus 74 is 1. 1 squared is 1. And 68 minus 74 is negative 6. Negative 6 squared is 36. When I add these 4 numbers together, I get 230. Divided by 3 gives me roughly 76.7. Okay? So then, so 76.7, that's the variance. To get the standard deviation, then I need to take the square root of 76.7. Okay, so the square root of 76.7 is 8.76, okay, roughly. So that would be my sample standard deviation, okay? And now they want us to answer the question, is this an overestimate or an underestimate of the population standard deviation? So the population standard deviation was 9.74. We got 8.76. That's an underestimate, right, because this number is smaller than the true standard deviation. The true standard deviation is where I use all the values, right? And I underestimated this by about 0.98 beats per minute, okay? So, and by the way, it's a good idea to check and see, how far off was I, and if you're able to. Sometimes you're not able to. But that tells you how good the sample was. Now, by the way, if I is sitting at the mean, 74, and I add 8.76, then I get 82.76. Okay, well, the biggest number that I had was 86. Now, if I'm at the mean, 74, and I subtract 8.76, that gives me 65.24. Well, the smallest number that I had was 67. So why am I less than that? Well, all that means is that the data that is to the right of the mean is going to be it's going to be more distant than the data values that are to the left of the mean. Okay, so I got a note here that the data is spread out more from the mean on one side. On the other side, 67 and 68 are more distant from the mean than 75 and 86. Okay, so 75 is right next to 74, right? So 86 is pretty much the only one that you're counting there. So 67 and 68 together are more distant than 75 and 78 and 86. Okay, that's all that means. So I don't want to be like way outside of the bounds on both sides there. Otherwise there's a mistake somewhere that I go to. So with the range, and by the way, they weren't asking for the range here for the sample, but the range is something we can easily get. If I take 86 minus 67, that would be a range of 19. 19 is not a super huge number, not a super minuscule number, so I shouldn't get a standard deviation that is either one of those two extremes. And that's exactly what happened, 8.76. So it's not a super huge number, not a super minuscule number. So to me, at least this number sounds right, okay? why don't we go ahead and stop right here in the notes, and I'll pick up with number 7 in the next video.